Hi there, and welcome back to Triplicate and to the third part of the filter enhancement section of the synthesis tutorial. Again, all these filter enhancements are me experimenting with ideas and are not things I have actually implemented in synthesizers. And in the first part of these filter enhancements we tried to make our filter sound a bit warmer with limited success. So let's try again, only this time we are going to use a 4-pole low-pass filter of the type used in a lot of analog synthesizers such as the Moog. And this is Bob Moog's original patent, and you can see although he's using these transistors as resistors, there are 4 capacitors, so it's 4 filters. So let's have a look at how this 4-pole filter works. Okay, so what we actually have is 4 simple RC low-pass filters in series. And we have with that some feedback. And we have some scale on the input, and that is the output. And before we get into looking at how this works, let us actually just consider one RC filter and see how that works. Okay, so here's our RC filter. And let's say our output is Y and our input is X. And that is R and that is C. And that's our current. So Ohm's law gives us X minus Y over R equals I. And the equation for a capacitor is Q equals CV. So assuming we're charging with the constant current I equals C delta V, the change in voltage. Now, if we were trying to solve this mathematically, we wouldn't use delta V, we'd use dV and do calculus, but we are sampling, so we are trying to calculate a new Y, we'll call that Yn, from the input X and an old output Yn minus 1. So delta V equals Yn minus Yn minus 1. Substituting for I, X minus Yn minus 1 equals RC times Yn minus Yn minus 1. And I've got out of paper. So let's rearrange this. We get RC Yn equals X minus n minus 1 plus RC ny, come on, n minus 1. And we can divide by RC throughout and we get yn equals 1 over RCX plus 1 minus 1 over RC yn minus 1. And if we now replaced 1 over RC with, what should we say, smooth or alpha or whatever I've called it in various equations, that is a simple smoothing equation we've tried before with the parameters. That's probably the simplest digital filter you can make. So let's build one of those and see how it performs. Okay, so a quick look at the code. So outcur is yn in the equation we've just developed, and outlast is yn minus 1, and time const is 1 over rc. So 1 minus time const time outlast plus the new input times time const is the output current, and then we save the current to the last. So we can calculate the next sample, and then samp 0 and samp 1 are the sample values, and samp 0 is the input and samp 1 is the filter. So if we now go in here, this is what we get. The top one is the input and the bottom one is what goes through the filter. So let's have a look at what it's doing. At very low frequencies, not providing much attenuation, and it's not changing the phase. At very high frequencies, that's the top. So the filtered output phase is nearly 90 degrees behind the input, and it's providing a lot of attenuation. Okay, and here we have a point which is of special interest to us. You can see I've selected here between the top of the wave and 0, and you can see here the filtered wave is, the top is about the middle of that. So the phase lag on the filter is about 1/8 of a cycle. So that's 1, 2, 3, 4. And you can see what I've just done with the mouse pointer. If we have 4 of these, identical ones of these in series, the output will be half a cycle behind the input, and that is significant. So let's also measure the attenuation of the filter at this point. So we are looking at maximum sample value is 25,000. Place 17386. Call that 174. Okay, so let's check what that attenuation is. It's 17.4 divided by 25 equals, we'll call that 0.7, shall we? Near enough. So at the particular frequency we just considered, which is incidentally the cutoff frequency, this point, if say we're putting a sine wave in, we're characterising the filter, we're always considering sine waves. We're putting a sine wave in. This point is 180 degrees phase difference to this point, or out of phase. So if the feedback is negative, then that will reinforce this, and we will get actually an amplification at that frequency. Okay, so let's do a couple of calculations to see what that needs to be and the relationship between the feedback and the amount of resonance we get. So to do these, let's say the output is Y, the input is X, this is K, and this point, the actual input to the 4 poles, is A. So firstly, let's consider DC, constant level input, so there is no filtering. So at this point we are saying Y equals X. However, we also know that Y equals A. But we are also saying A equals KX minus, because the feedback, which we're calling F, we're saying F is positive, so we're always taking minus F here. Minus Fy. But A, Y and X are all the same in this case. So 1 equals K minus F, and we want K, so K equals 1 plus F. So this scaling factor needs to change with the feedback. Fair enough. So now let's consider what happens at resonance. So we know at resonance each of these is about 0.7. So Y equals 0.7 times 0.7 times 0.7 times 0.7 A. And we know the phase is 180 degrees out. And 0.7 times 0.7 times 0.7 times 0.7, well 0.7 is, it so happens, it's actually the square root of 2. So 1 over the square root of 2. So 1 over the square root of 2 to the power of 4 is a quarter. So we say Y equals minus a quarter A. But we also know this equation, from this equation here, A equals K, which is 1 plus F minus Fy. Okay, so far so good. And substituting for A here equals minus 4Y, which gives, that's X, which gives us 1 plus Fx equals F minus 4Y, and the resonance, res equals Y over X at the resonant frequency equals 1 plus F over F minus 4. We want to be able to set a feedback value depending on an actual resonance, not some sort of quite complicated relationship. And okay, to be accurate, because Y is always X inverted, resonance R is minus Y over X. So rearranging that because we want to calculate the feedback level from the resonance. F equals 4R minus 1 over R plus 1. So now we have all our parameters for our filter. Let us build a 4-pole filter with feedback and see how it performs. Okay, a very quick look at how this works. And ignore the fact I'm calling it the filter twice with to generate cold and warm values. We're all looking at cold values at the minute just to get it working in its most basic form. So here you can see the resonance to feedback calculation, and the filter just takes straight feedback. And if we go down here, and we have a do stage function which does one pole of the filter, one RC filter, and we call 4 times. And at the top here it takes the in and multiplies it by feedback plus 1 and takes the feedback from the last stage. And the do stage is, as we said, okay, warm time constant, don't worry about, that's coming. So if we give that a whirl, okay, and fire it up, here we go. And there you can see we have a resonant filter. Just out of curiosity, let's see how, if the resonance comes out where it should be. Okay, yes, so here we've set the resonance to 4. So let's have a look. So the input is 5,000 here, and the output is 28,000. So it's actually a bit more resonant than we would imagine. However, there are issues with doing the filter this way due to the lag down the filter, so we're not surprised that it doesn't behave exactly how we would expect. And just out of curiosity, how does it compare to our state variable type filter? Well, here we have the 4-pole filter at the top and the old state variable type filter at the bottom, and you can see the 4-pole filter seems to give a sharper resonant peak, but apart from that, yeah, pretty similar. There's been somewhat of a break at this point due to spending quite a lot of time playing around with this 4-pole filter, and also due to the birth of our second grandson. So here are basically some conclusions. So here is the 4-pole filter against the original state variable filter for 4 different frequencies. That frequency, and immediately we look at that and say, what is that going on there? That frequency, which is higher, that frequency, and you can already see the resonance is starting to go down with the higher frequencies, and that frequency, and the resonance we would expect to be the same for the 2 filters, and you can see it's well down there. And I sort of set this filter up to work with the Mean Green PC simulation program, and
Okay, and here we are. We've got the resonance turned pretty well up to maximum, and we're gradually raising the filter cutoff frequency as this little sound file plays. So let's have a play of this. And you can hear there's some strange warbling going on with the lower cutoff frequency settings at the start, and you can hear by the last note the resonance seems to have completely vanished. There's no sort of sound of the resonance at all.
So our 4-pole filter doesn't work as well as we would like, and this is because we are sort of granular in time, if you like. We have a sample rate, and there is a lag down the filter that you wouldn't get in an analog electronic filter, which stops it working properly, and there are ways around this, but I don't propose to go into it any further here. And given that it doesn't work terribly well to start with, and the fact that I did actually try sort of adding some non-linearity to it and just got a terrible noise, I don't propose to actually bother looking at trying to make it warm or fat or whatever. And I also downloaded some TB303 samples and had a look at those, and I started to come to some slightly different conclusions as to why these analog synthesizers sound the way they do, but that will have to be a whole separate video. So I'm gonna leave this one here with a basic look at how 4-pole filter with feedback, which was the type of filter used in certainly the earlier analog synthesizers. And that I am going to wrap it up for these synthesizer tutorials. As I say, these last 3 have been really me experimenting with stuff rather than telling you what I have done and implemented in actual products. But I hope it's been interesting, and I do plan to continue this work, but I'll start a new series of videos more aimed towards experimentation. So, as I say, that's it for the synthesizer tutorial videos. Hope you've enjoyed them, hope they've been useful and informative, and look out for other synthesizer videos. I'm sort of enthused now and want to go back and play with synthesizer stuff a bit more, so there will be more. So for now, it's goodbye from Triplicate, home of interesting electronics. Goodbye.